Alright, so we're going to continue our discussion of polynomial functions today. We're going to do a little bit of review to start off, though, just to make sure that we remember everything from last week. And we're going to talk a little bit about graphs of polynomial functions. And what I'm going to do is I'm going to give you graphs of some functions, and I'm going to ask you if they could be polynomial functions, and if not, why can't they be? So I'm going to put a couple functions up here. There's one. And let's see, this is another one. Indicate they do keep continuing there. And then I'll put a third one down here. And let's actually, with this last one, let's just pretend that that happens. And maybe we have and a close star right here. All right, so let's just run through these three examples right here and tell me, each of these, could they possibly be graphs of a polynomial function? And why or why not? So this first one here. This one right here, could this possibly be a polynomial function? Why is it a polynomial function or not a polynomial function?
I'm guessing no.
Why not?
Because how they will point at a corner.
Yeah, so we know about polynomial functions, they have to be both. They have to be what?
Continuous
and
uniform. The word I can't get it.
Smooth. You're getting at the right idea, but yes, they have to be smooth. This one is not smooth. It has that. And so what makes it not is this little corner right here. That's not. The polynomial function can't have any corners. They're nice and smooth, which is one of their properties. The next one, so this is not a polynomial. What about this one right here? Could that possibly be a polynomial?
Yeah.
Yeah, there's nothing that says that's making it not. It's both smooth, right? There's no corners or cusps or anything like that. And it's also continuous. There's no breaks in the function. And what about the last one here, this one right here? Yeah, this is not a polynomial function because it is what? Not what? Not continuous. As we see right there. So polynomial functions are they're not necessarily unique in that they're continuous and smooth, but it is a property of polynomial functions that they're both continuous and smooth. There's many functions that are not one of those two things. They either have a corner or they have a discontinuity of some sort, and polynomial functions are not like that. So that's how we can identify a graph of a possible polynomial function just by sort of taking a look at it. Okay. Okay, now let's talk a little bit about turning points. Which your book calls these turning points. Once you get to calculus, we're going to really refer to them as relative extrema. Relative extrema is a more technical way of referring to them instead of saying turning points. And it just sort of refers to both, and relative extrema is sort of referring to both relative maximums and relative minimums. So, for instance, if we were to look at the following function, what a turning point is just any point the function turns around. It goes from increasing to decreasing, or it goes from decreasing to increasing. So this function right here that I just drew has two turning points, right? Also known as relative extrema. This one right here is a turning point, right, because it goes from increasing to decreasing. We also call this a what? A relative what?
Maximum.
Yeah, this is also a relative maximum, and this is a relative minimum, okay? And then a function like this has how many turning points?
4.
4 turning points. So knowing what a turning point is not super technical. In this book, we'll call them turning points in the future, and when we get to calculus, we'll start calling them relative extrema. And so, interestingly, we can draw some conclusions about the number of turning points a function has based upon the order of the function. So, for instance, if I have a function like a really basic function, so let me just give this a title, so turning points versus order of polynomial. So let's look at two functions. The function f of x equals 3x to the fourth. That's a power function because it's a monomial, right? But it is to the fourth power. And then we'll look at one that's not a power function, which take out this here. So let's look at 2x. I'm going to need more room for that. We'll look at the function f of x equals 2x to the fourth minus x cubed minus 42x squared minus 29x plus 70. All right. So what I want you to do is go ahead and on your graphing calculator graph both of those functions for me, which we'll also do on the screen here in a second, and we'll look at how many turning points they are, and maybe we'll come up with some sort of a rule as far as how many turning points a function of a certain order might have. So if we're able to graph those functions, we go ahead and take a look at them. 3x to the fourth is just a basic power function, and because it's an even power function, we know it sort of looks like a parabola. Maybe a parabola with steeper sides and a shallower and a flatter bottom. Sorry, but that means it only has one turning point, right? The other one, on the other hand, is also a fourth power. They're both fourth order polynomials, right? But this other one has 1, 2, 3 turning points, right? And it turns out the number of turning points is always going to be equal to n minus 1 if n is the order of the polynomial. Sorry, I need to rephrase that. Not the exact number, but the most number of turning points, or the greatest number of turning points is n minus 1. Of a polynomial function. The greatest number of turning points is n minus 1 if n is the order of the polynomial. So what we have here is a fourth order polynomial then. This is a fourth order polynomial, right? If n is 4, n minus 1 is 3. That means the most number of turning points that either of these functions could possibly have had was 3. And this one has the maximum number of turning points that a polynomial function of the fourth order could possibly have. So that's a theorem that we're going to be using from this point forward. You can't really, there's a really easy way to prove it using calculus. Of course, we haven't gotten there yet, so we're not going to worry about that. But it is very easy to prove that that is the case. And you'll do that in calculus class. The last thing we want to talk about that's interesting here, that's also true about these two functions, is they behave similarly when x gets very large, right? So, for instance here, let's look at two separate functions. Let's talk about n behavior now. This is the last sort of property that we're going to address today. The n behavior of polynomial functions. And what we're talking about when we're talking about n behavior is essentially what happens when x gets large. Like, how does it behave as x gets really big, the function itself. What happens to the y value? Right. So let's look at two functions as examples. The first one will be f of x equals 2x to the fourth. And the other one will be that same function that we just looked at a second ago, which was 2x to the fourth minus x cubed minus 42x squared minus 29x plus 70. That one takes a while to write out. Now, we go ahead and we graph both of these functions. Right, the first one we know, once again, it's a fourth order power function, right? So it's going to look sort of like a parabola because it's an even power. And the other one we just had a second ago. I'll just go ahead and regraph that. And that one looks roughly like this. And what we're going to notice is that when x is small, sort of in this area right here, they do behave quite differently, right? In the fact that there's only one turning point here, and there's 3 turning points over here. And then so on the graph here, just to give you a sense of scale, for the first one here, that's -4. That 0 happens at -2. This 0 actually happens at 1, and this 0 happens at 7/2, or 3.5. So those are all what we would consider very small values of x. They're not very large numbers, right? And so around these small values, the function behaves very differently than this function. However, when we look at the ends here, as it goes off to infinity, once we get past this point here and we go out to the left over here, or we go out to the right over here, we see that it sort of goes back to behaving just like this function, right? They both sort of take off to infinity, right, at similar rates. Right? And that's going to be true for all power functions of the same order. All right? So as far as n behavior is concerned, right, any two polynomial functions of the same order with the same coefficient on the highest power. Like in this case, what I mean by that in this case is that the coefficient on the highest power here is 2, the coefficient on the highest power over here is 2, so they're both the same order and they have the same coefficient on the highest power. If that's the case, any two polynomial functions of the same order with the same coefficient on the highest power will behave the same when x is large. Will act the same if x large, I'll say, just to be able to keep that on the screen there. So any two polynomial functions that have the same highest order, in this case they're both order 4, the same coefficient on the highest power will act the same if x is large, even if they act very differently when x is small. So that's what we call n behavior, and we can use that to give ourselves an even better sense of, you know, just exactly how big or small how a function behaves, when x gets really large. And so let's go ahead and actually just summarize that last rule about n behavior a little more formally. So in formal manner, we'd say for large values of x, the graph of any function, of any polynomial function, right? A sub n x to the n plus a sub n minus 1 x to the n minus 1. And then we'll go dot, dot, dot. This will represent any polynomial function. The graph of that, just any general polynomial function will resemble the graph of whatever the highest order term is, which in this case is a to the n, x to the n. Right, will resemble that power function. And so, once again, that's going to allow us to sort of analyze some functions better. So let's look at an example here. I have the function f of x equals 2x plus 1 times x minus 3 squared. This is a polynomial function, right? It's just in what form? What do we call this when it's all multiplied out like that? It's not like individual terms, right? It's two binomials multiplied together. Factored form. So what we're going to do is we're going to analyze, we're going to call this analyzing, the graph of f of x. Right? Which essentially means sketch a rough, or sort of a rough sketch of the graph of that function by identifying some basic properties of the function using the information that we just developed here. All right. So the first thing we can do is if we have the factored form of the function, what's one property of the function we can figure out right away?
Zeros.
The zeros. Yeah, we can figure out the x-intercept. So if we go ahead and set f of x equal to 0, we can right away find out where it crosses the x-axis. So we'll set that equal to 0. Whoops. Oh, you little. So we set that equal to 0. Right. And since it's already factored out, we know that 2x plus 1 has to equal 0 or x minus 3 has to equal 0. So we get the fact that either x could equal negative 1/2 or x equals 3. Those are the two x-intercepts. Now, at x equals 3, what is the multiplicity of that particular root? It's x minus 3 squared. So what does that mean as far as multiplicity, and what does that tell us about the graph of the function? Versus 2x plus 1's multiplicity. Well, what is the multiplicity, first of all? It's the easy part. Multiplicity of x equals negative 1/2 is what? 1. What's the multiplicity of x equals 3? 2. Yes. So if the multiplicity is an odd number like 1, what do we know about that 0? Does it cross the x-axis or just touch it and then turn back around? If it's what? So if the multiplicity is odd in the case of 2x plus 1 to the first power, it actually will cross the x-axis there, right? So at negative 1/2, we know it crosses the x-axis, and at x equals 3, it just touches without crossing. So we'll just say doesn't cross. So those are the x-intercepts. What other information about the function can we figure out pretty easily? So those are my zeros. What other information about the function can I get pretty quickly? The zeros are the x-intercepts, right? What about the y-intercept? How do I get the y-intercept? If I get the x-intercept by setting y equal to 0, how do I get the y-intercept? Yeah, so we want to find f of 0, which in this case is going to be, if I make 2x plus 1 0, I get 1, right? And if I make x minus 3 0, I get negative 3. If I make x equal to 0 and x minus 3, and x equal to 0 and 2x plus 1, which will give me what? Positive 9, right? So the y-intercept is 9, and the x-intercepts are negative 1/2 and 3. So we're already sort of, I'm going to start drawing, or at least plotting some points for the graph of the function over here. So we already know that one of the x-intercepts is negative 1/2, one is 3. So one of them is right not right there. All right, so one of them is right there. Just erase all this and try this again. So one of them is roughly right there, and the other one is sort of, if this is 1, 1/2 is sort of roughly right there. All right, so those are the two x-intercepts, and we know that the y-intercept is 9, so let's just say 9 is up here. So it's going to cross up there too. Right, so let's go ahead and talk about some of the other ideas. So we talked about multiplicity. We identified the the zeros. Let's talk about turning points and end behavior to help us understand more what this function might look like. So first of all, turning points. How many turning points? What's the max number of turning points? What if I were to go ahead and multiply this out, what order polynomial would I get? It's going to give me an x squared term. It's going to give me an x cubed, just a regular x term. So what do we think? If I multiply this all out, I'm going to get a polynomial of order 3, right? Because this is going to give me a quadratic, x minus 3 times x minus 3, and then if I multiply it by another one, that'll be an x times an x squared term. It'll give me an x cubed term, right? So this is going to be an order 3, 1, meaning the max number of turning points is 2, 1 less than that. What is it going to look like as it gets really large? What is the end behavior going to look like? So the max turning points is 2. The end behavior is going to look like its highest order term. So I have to know its highest order term, right? And if I go ahead and multiply this all out, I'll save us the time. But you'd have to, once again, to multiply this all out, you have to FOIL this, right? And then multiply it by the binomials. So you're going to be multiplying a trinomial by a binomial. If you have any trouble with that, you need to review it, let me know at some point. But if we do go ahead and multiply that all out, what we'll end up getting is 2x cubed minus 11x squared plus 12x plus 9. That's the fully expanded version of that right there. And so my end behavior is going to be 2x cubed. It's going to look like a cubic function, 2x cubed, which means it's going to sort of ultimately, what does 2x cubed look like? It looks like this, right? So at the ends over here and over here, it's going to go up like this, and it's going to go eventually down like that. So it's got to end up ultimately going up like this when x gets really big, and then going down over here as x gets really small. That's definitely going to happen, right? And it can't have any more than 2 turning points, right? So what are possibilities for what it might potentially look like? Go up here, and then it can come down, and then it can come back up again, right? But it can't come back up again after that point because it can't cross the x-axis any more times, right? So, oh, and the multiplicity, right? At -1/2 it has to cross, and at 3 it just touches it. So what could it look like? It could go up here, cross the x-axis. At some point it's going to have to turn around, and then it goes down here, but it doesn't actually cross. It just goes back up, right? Because the multiplicity being 2. Does that make sense? And we could also look at, you know, where is this going to be positive and where is it going to be negative? That tells me where I'm below and where I'm above the x-axis, right? So I could try like a value to the left of 1 here, right? Try like -1, see what that's going to make this. It's going to make it, if we tried that, we'd see that it would make this negative, so we're below the x-axis. So if we go to the right of 1/2, right, it's going to be above the x-axis, it's going to make this positive, right? And then it's going to stay positive for the rest of the time. So using all the information we've sort of gathered, we can sort of say that this polynomial's got to look something. Let me try that again. I really wish this would let me back up. Oh, nice. Okay, so that's fine. Let me just try that entirely over again. So this function has got to look something roughly like this, right? It's got to have two x-intercepts. The multiplicity of 3 is even, so it's got to turn around right there. Multiplicity at -1/2 is odd. It's got to cross right there. It has to cross the y-axis at 9. That gives it how many turning points? 2, so that's okay. That's not more than it has. And then you can finally, so when you get done with this, we're going to, like I said, we did this, or you saw, we did this all without a calculator. When you get done doing it without a calculator, right, go ahead and confirm that that actually is the graph by graphing it in your graphing calculator. And if it looks like that, then you know you are on the right track. Okay? So I'm going to have you go ahead and tackle this on your own now. Take this next example here. I want you to go ahead and do your best job to graph this without using a calculator. Right? So you're going to go ahead, find your x-intercepts, find your y-intercept, identify how the maximum number of turning points, figure out what the end behavior is going to be, and use all of that information to draw a rough sketch of the graph. It doesn't have to be perfect. You're not going to necessarily know where the turning points occur, where are the relative minimums and maxes, where they actually occur. You won't be able to find that, but just sort of approximate it, right? And then when you get done sketching it all out, go ahead and graph it on your graphing calculator and compare just to see if you got it right or not. Okay, so try to do this entirely by hand without a graphing calculator before busting out the graphing calculator. All right, so let's start off by identifying the zeros. We can just sort of look at the polynomial and just sort of pick them out there. What are my zeros going to be? 2. -1, -7, yep. And at 2 and 7, we know that it does what? Crosses, yeah. And at 1, it doesn't cross. Okay, my y-intercepts. F of 0 ends up being -2 times 1 squared times 7. That gives me -14, right? You can do that with all that without having to multiply it out ahead of time, right? Just plug in x for 0 for x, and it's nice and easy. So we have the y-intercept, the zeros, the y-intercept. How many possible turning points could I have? So there has to be less than or equal to 3 turning points because it's going to end up being a 4th order polynomial when I multiply it all out. End behavior. If you multiply that all out, your highest order term is just going to be x to the 4th, right? So the end behavior is going to be x to the 4th, so it's going to look like that. Looks going to look like x to the 4th when it gets really big. And so with this information, we can draw a general sketch of it. And so I like to start off by doing the end behavior and saying, okay, well, when it gets really large, it has to go off up here and up here, because that's what x to the 4th does, right? It grows to in positive infinity on either side because it's an even power function. And let's go ahead and mark off the x-intercepts and the y-intercept. So I start with the turning points, and then I go ahead and mark off my intercepts. So 2, -1, -7. So -7 there, -1, we have 2, and so there's one of the intercepts there at 2. We have one at 1. We have one at -7. And then the y-intercept's -14, which, just for the sake of simplicity, I'm just going to make my scale so that -14 is right there. And so at -1, it doesn't cross, right, at all. So I know that sort of between where it crosses at 14 and -1, -1 sort of has to look like this. So you can sort of, let me try that again. Hey, I wish. The eraser only works when it's not convenient. 1, 2, 3, 4, 5. All right, so we know at 1, it's got to turn around. And I'm just guessing it's under because it has this y-intercept down there. Once again, if you're not sure where the function is above or below the x-axis, right, plug in a test value, right? Just like we did with the quadratic inequalities to figure out whether it's above or below the x-axis, we plug in a test value in between and figure out whether it's negative or positive. But I'm going to guess it's going to look something like this, right? And then it's got to have a turning point somewhere here as well, so I'm going to go ahead and cross that x-axis. And so my guess is that the function looks roughly like that, and you can go ahead and graph it. And if you put it in your graphing calculator, indeed, it does end up looking pretty much like that. Now, the last question that we would like to be able, or some questions that we sort of, unless we really use our graphing calculator at this point, we're not going to be able to answer are, and these are interesting questions, well, we have these turning points. Where do the turning points occur? Right, we're going to, in the next part here, we're going to use our graphing calculator to look at the minimums, the relative mins, these two right here, and the relative maxes. What point, well, this one is pretty obvious, right? It has to, you get one, if you have an even multiplicity root, like x plus 1 squared, that'll give you one of the turning points right away, because you know that has to be a turning point, because it can't cross the x-axis. But these two, because they're not on zeros, unless we use calculus or our calculator, we can't really figure that out. So we're going to use our calculator to figure out, well, where does this turn around? And then we can figure out intervals over which the function is decreasing, when it's increasing, what is the domain, what is the range. We can answer questions like that. And so we're going to ultimately use our graphing calculator to finish answering those types of questions in the next part here. So we just got done trying to draw a rough graph of a polynomial function without using a calculator. And if the function is factorable, as all the ones we've seen have been, then that's not so difficult to process because you can easily locate the x-intercepts, the y-intercepts, and so forth. And you can make an educated guess at what the general sort of curvature of the function looks like using what you know about multiplicity and behavior. But sometimes if you can't find the x-intercepts, then that makes it very difficult. And then we really have to go and rely heavily on our graphing calculator to locate all of these different things. So for instance, so we're going to be analyzing, let's go ahead here, we're going to be all right, eventually, we're going to be analyzing polynomial functions with our calculator. Which essentially means that obviously we're going to graph it using our calculator. That's going to be the first step. But we want to also use the calculator to locate all of the important points. So one of our major goals is to locate all critical points. And by critical points, I mean we want to locate all of the intercepts, of course, x-intercepts and y-intercepts. We also want to locate all of the turning points, right? And so that we know where those occur. And then that's going to allow us to figure out things like domain, range, where is it increasing, where is it decreasing, and so on by looking at the graph. All right, so let's start with the function f of x equals x cubed plus 2.48, whoops. 2.48x squared, there we go, minus 4.3155 x plus 2.84406. So especially with all the decimals here, you can see that, if I could factor this out, I could find the x-intercepts, but you're not going to be factoring it out with all those decimals there. So what you're going to do is you're going to go ahead and plug it into your calculator, and we'll graph it with our calculator initially just to get a rough sketch of it, and then we'll identify the x-intercepts, exactly where they are located, and the minimum and maximum values and exactly where they're located. So if I go ahead and I graph that function in my calculator, I'm just going to go ahead and draw a very rough sketch of this. And it is going to look something like that. So I want to figure out where, it definitely has one x-intercept. I want to figure out where is that. There's one y-intercept. I want to figure out where is that. There's two turning points. I want to figure out where those both happen to be. And then once I've done that, I can answer questions about domain and range, like I said, and also where is it increasing, where is it decreasing. We'll get some practice with interval notation. Okay, so the first thing, let's go ahead and we're going to use the zero finder on our calculator to locate the zero. Actually, we don't, before we do that, what is the y-intercept? Because we don't actually need the calculator for the y-intercept ever. Yeah, if we plug in 0 for x, f of 0 gives us 2.84406. So we know that already, that point right there, right, is the point 0, 2.84406. So for that one's out to a lot of decimal places, but for the mins and maxes here and the x-intercepts, you can find those to, let's say, 2 decimal places. We don't have to go out to that many decimal places. So that's the y-intercept. We also want to find, let's go ahead and use our zero finder to find the x-intercept. So use the zero function on your calculator. So this x-intercept occurs at negative 3.79, roughly. Okay, so we found the x-intercept. Now let's go ahead and we're going to use the max and the min function to locate this relative max and this relative min, both of our turning points here. So let's go ahead and do that now with our calculator. All right, so if we go ahead there, okay, so we found the relative max, so we're going to put that in now. So the maximum is at negative 2.28, 13.36. That's the one right there. Right, now we want to go ahead and find this minimum right here. So we have a min at... So using the min function in our graphing calculator, we find 0.631 is that minimum right there. So we have the maximum, the minimum, the y-intercept, the x-intercept. That's most of the relevant information that we need. And from that now we can make, we can say certain things about the domain and the range. So, for instance, the domain, well, in this case, sometimes the turning points, we need them to determine domain and range. In this case, domain and range is relatively easy. It's going to be what for both? Negative infinity to infinity, right? So yeah, the domain's negative infinity to infinity. The range would also be negative infinity to infinity in this case. And that's because, you know, it goes down forever and then it goes up forever. So it's going to cover all of the y values. And it's also going to, just like any other polynomial function, it's going to have a range of infinity as well, because you can plug in any value for x to this. And so but we can't answer the question, where is it increasing? Where is my polynomial function increasing, and where is it decreasing? Right, so on what intervals would you say, Kevin, it's increasing?
From 0, point, wait, so from 0 until infinity.
So the function, if I look at it, it's increasing from negative infinity all the way to this turning point, this relative max right here, right? And then it starts going down again. So over this interval, negative infinity to negative 2.28, it's going to be increasing. And then I'm going to union that with the other interval that it's increasing, which is going to be from, it's decreasing from here to this other turning point. And then from negative 0.63 off to positive infinity, it's also increasing. So I'm going to union these two. So negative 0.63 to positive infinity, it is also increasing. And the only interval over which it's decreasing is in between there, from negative 2.28 to 0.63. Okay, so we can answer domain, range, increasing, decreasing. All of those two questions, domain, range, increasing, decreasing, can be answered exactly if we're able to find the all maximums, minimums, all the turning points between those two, the x-intercept and the y-intercept, right? And then we can get a very accurate graph of the function and answer some very specific questions about the function as well. Okay? So we've seen polynomial functions that have been in their fully factored form. Those ones are pretty easy to analyze without using a calculator. We just saw a polynomial function in an unfactored, fully simplified form that we couldn't really factor, so we had to use our calculator. But sometimes we're going to see polynomial functions that are that are not factored but are factorable, and we want to go ahead and fully analyze them. So I'd like you right now to go ahead and fully analyze the following polynomial function. So analyze and graph, and I want you to do this all without your calculator. Analyze and graph the function f of x equals 3x cubed minus 6x squared minus 9x. So you're going to have to go ahead and graph it, right? And when you're done graphing it, sorry, you're going to go ahead and factor it. That's what I meant to say. So factor it so that you can get your x-intercepts, get your y-intercepts. Try and generally get the graph of the function, what it looks like based on the multiplicity of the zeros and all that. And once you've done all that and you've sketched out a rough graph of the function, then go ahead and compare it to the graph of the function in the calculator, graph it in the calculator, and then use your calculator to locate any turning points, right? And locate those and answer the question, what's the domain, what's the range, and where is it increasing, where is it decreasing? So with this function, we want to go ahead and we want to factor it out first. So take out your 3x here, that's your GCF, leaving you with x squared minus 2x minus 3. And then go ahead and factor that, and you're going to get x minus 3 times x plus 1. Now it's fully factored, and so your zeros, set that equal to 0, your zeros are 0, negative 1, and 3, right? All multiplicity 1. And so you have your zeros, your y-intercept is going to be 0, right? All right, and so if we go ahead and we draw a graph of this, a rough sketch of this function here, goes to the origin, then we have negative 1, we have 1, 2, 3 up here, right? So it's got to go through this point right here. Oops. The point negative 1 right there. It's got to go through the point 3. And it's got to go through right to the origin there as well. So, looking at this, turning points. We know that there has to be no more than 2 turning points with the cubic function. So max of 2 turning points. And is it going to cross all of the x, all the zeros? It's going to cross at all of them, right? Because the multiplicity is 1. All right, and so we got to figure out where is it above the x-axis and where is it below the x-axis. We can go ahead and make a sign chart for that. So let's go ahead and practice making a sign chart. So we have negative 1, we have 0, and we have 3, and we want to know, is f of x positive, negative, or 0? And in the fully factored form here, it's really convenient. What I'm going to do here is I'm going to think of a test value to the left of negative 1 here. To the left of negative 1 could be negative 2, right? And negative 2 is going to make this positive, and I'm going to look at the fully factored version of this. That's going to make this positive, this negative, and this also negative. So, sorry, this is negative as well. So, yeah, because negative 2 times 3 is negative. This factor is going to be negative. Negative 2 minus 3 is negative 5. Negative 2 plus 1 is also negative. So a negative times a negative times a negative is a... So that means everything in that interval from negative infinity to negative 1 has to be below the x-axis because it's negative. Now let's go ahead and use a test value between negative 1 and 0. Negative 1/2, for instance, is going to make this negative. This will still be negative. This now becomes positive, though. So a negative times a positive will give me a positive value, right? And so that means it's going to be above the x-axis between negative 1 and 0. And then we look at this last, between 0 and 3, 1 is an easy one to use. That's between 0 and 3. So that's going to make this positive, this negative, and this positive. So a positive times a positive is negative. And then lastly, 4 would be a good test value for this region right here. So 4 times 3 is 12, that's positive. 4 minus 3 is positive, that's positive. Positive, positive, positive is positive. So like I said, we can use a sign chart to tell where it's above and where it's below. So it's got to start below and end. So it starts below the x-axis. And we also know that from, we can think of the end behavior, right? What's the end behavior?
X cubed.
Whoops. The end behavior is x cubed, meaning it has to get really large down there and really small down there and really large up here, right? Because we know x cubed sort of looks like this, right? So when x is big, it's going to have this sort of same behavior like x cubed. And so it's got to do that for sure. And then we're just going to go ahead and sort of connect the dots. It's got to cross there, it's got to come back through, and then it's going to come back up and go up there like so. So we know that it roughly looks like that. And if you go ahead and graph it in your graphing calculator, you'll see that. And so our calculator confirms this, and now we're going to use our calculator to locate the relative max right here and the relative minimum right here. And so we see that our relative max right here is going to be negative 0.54, 2.63. So that's our max, and our relative minimum right here, if we use the min function in our calculator, will be 1.87 and negative 18.19. So that's a relative min right there. And from that, we can determine where the function is increasing and where it's decreasing. We know the domain and the range is easy for this one as well. We know it's going to be all real numbers for both the domain and both the range. And I'm just going to say it since I don't have any room to really write it in here. But the function will be increasing from negative infinity all the way up to the maximum at negative 0.54. And it'll also be increasing from the minimum right here all the way out to infinity, so from 1.87 to infinity. So if you do negative 0.54 to infinity union 1.87 to infinity, that'll be the domain over which the function is increasing. And the function is decreasing from negative 0.54 down to 1.87. Okay? That should do it for today. I'm going to go ahead now and give you the assignment for tonight. So this is the assignment for tonight. It's from the handout that I handed out last Tuesday. There was no new handout for today, just those problems from that handout. And I hope to have a practice exam for you guys from Chapter 2 in the next day or two here with the solution, so you can take a look at that. Since we just finished up Chapter 2, we're in Chapter 4 now, but like I said, I wanted to give you a practice exam, and I will have that in the next day or two. Have a great day.